So another tool that astronomers have available to them that uses visible light as its medium is called a spectroscope. It's a tool that is used to capture and measure different wavelengths of visible light. So what I mean by that is when you think of the full electromagnetic spectrum, there's actually very little of this that our human bodies can really sense. To some degree, we can sense ultraviolet. If we get too much of it, you can get a sunburn on your skin. Infrared, we can kind of sense as heat. But visible light is the easiest one for us to sense just by use of our eyes. We're able to see most, if not all, colors of the visible light spectrum, but it really is no different than any of the other range of electromagnetic radiation aside from its wavelength. We have shorter wavelength electromagnetic waves over here, longer wavelength over here, and visible light kind of lives near the middle here. But this is what the optical telescopes as well as the spectroscopes is really tasked with collecting. So I'll talk about how a spectroscope works in just a moment. In the meantime, our good buddy Bill Nye explains a little bit about the history of spectroscopy.
In the 1850s, Robert Bunsen and his research collaborator Gustav Kirchhoff conducted a series of experiments to determine why substances emitted specific colors when placed in a flame. The color they determined indicates what elements are present in the substance. For example, if sodium is placed in a flame, they observe shades of yellow. Copper, shades of green. Strontium, shades of red. That was a good one. While watching the experiments, Kirchhoff was reminded of how a prism spreads light into a rainbow of colors. So, using a prism and the pieces of a small telescope, Bunsen and Kirchhoff built the first spectroscope, an analytical device they hoped would help them see the spectra coming from heated substances. And it worked. As an element was put into the flame of a Bunsen burner, the light from the heated substance passed through the prism of the spectroscope, where it then spread into a ribbon-like spectrum of colors, riddled with dark lines. The combinations of bright colors and dark lines were like barcodes indicating what atoms were present. When burned, each element produced a completely unique spectrum. Using their spectroscope, Bunsen and Kirchhoff were able to discover two new elements, cesium and rubidium. One day, Bunsen and Kirchhoff decided to test their invention with sunlight. It produced a spectrum that featured two lines that were identical to those in the spectrum produced by sodium. Bunsen and Kirchhoff had discovered the presence of sodium in the sun, 93 million miles away. Suddenly, scientists had a tool to help them study the chemistry of the heavens.
Liftoff. We have liftoff.
Today, the legacy of this great discovery lives on in the exploration of space. A form of spectroscopy is being used to study the atmospheres of planets, to search for signs of water, signs of life.
All right, so with that, here's a little overview of what a spectroscope looks like. Ours are made out of kind of triangular-ish piece of plastic. Very simple machines, no moving parts. Has one tiny little slit opening here to allow light to come in. Then that light is transferred to a plastic prism where it's broken up into its components or ingredients to make that light. And then those components are transferred to what's called a diffraction gradient that basically measures the wavelength of each color of light that is visible. So very simple machines, but that's kind of what's going on inside of it. This is a little summary of what I just talked about. You can pause here to jot those ideas down if you need to. And then we're going to slide down to talk about what it is you actually see when you look through a spectroscope. So I'll show you pictures in just a moment, but a quick overview here. Continuous spectra is like the full rainbow effect. Roy G. Biv, if you're not familiar with that, it's all of the colors of the visible light spectrum arranged by wavelength. You have red, which is the longest wavelength, followed by orange, yellow, green, blue, indigo, and violet, which has the shortest wavelength. A continuous full rainbow spectra is created by a glowing solid. An example of a glowing solid that would give off light that you may be familiar with is an old incandescent light bulb that has one of those metal spirally filaments inside of it. A second type of spectra that you may see is called emission. Sometimes it's also called bright line spectra. These are illustrated as kind of a dark or dim background with very bright sections or lines of color. And again, that's made by a glowing gas. I'll show you a picture of that in just a moment. The third option of what you could see is called an absorption, or sometimes referred to as a dark line spectra. This appears at first glance very similar to the continuous spectra in that it has a full or almost full rainbow effect, separated by missing pieces or black bands that kind of blot out part of the rainbow. This one is a little more complex to make as well. It's made by either a glowing solid passing through something like a cooler gas, like an atmosphere, or a relatively cool gas that is giving off visible light. So in our case, a fluorescent light bulb will kind of mimic that. In real life, though, the sun and other stars would give off this type of light, as well as light reflected off of planets. As that light passes through a planet's atmosphere, some of those varieties of light may be absorbed by the gases that are present in that atmosphere. So I'll show you this spectra file here quick. This one goes in a little different order. Continuous here with the full Roy G. Biv rainbow. The second one on your list is actually down here, emission spectra. This is kind of a perfect example picture, but you may see kind of a dim background, not perfectly black like that, but a dim background, and then you have these brighter sections or lines of color. And then the third one on your list is the absorption, and you can see how at first glance it resembles very much the continuous spectra, but then it has these missing pieces here. Sometimes those missing pieces may be wider. They may in fact take up most of a particular color where that segment is just missing. All right, so then all we have left is what do scientists do with this information? So one thing they can do, surprisingly, with visible light only, is they can determine what elements make up the thing that they're looking at. For example, if they're analyzing a star in a far-off section of our galaxy or in a different galaxy, they're able to determine, based on the light information that they receive, what type of elements make up that object. And they can do that by comparing known elements. For example, hydrogen gives off a certain kind of color pattern or spectra versus oxygen. So they can compare those, and basically with the light from a star, they can determine a short list of ingredients that went into making that star and determine a lot about that star just based on the light that it's giving off. They can figure out roughly how old the star may be, what stage it's in its life cycle, and kind of the possible path forward for that star as well. Another thing that scientists can learn by looking at spectra is the temperature of the object. So when they're looking at objects in space, it can be a little counterintuitive because the cooler objects will actually give off a more red or red-orange color, whereas warmer objects will give off more blue light. And that all comes down to, remember before we talked about the electromagnetic spectrum, differences in wavelengths. Those wavelengths also have differences in the energy that is carried along with them. So cooler objects have the longer wavelength, red light. Warmer objects have the much shorter wavelength, blue light. And then the other colors kind of sort themselves out in between. And then finally, what I would consider maybe the most interesting piece of information that you can get by looking at spectra is you can determine direction and speed of objects that are or may be moving in space. This is an idea called Doppler shift. The idea is that red shift, a star gives off light more in the red end of the spectrum compared to what would be observed otherwise, and that's because the object may be moving away from the observer. So that means the visible light is being stretched or kind of pulled along as we view it, and that makes it shift more into the red end of the spectrum. Just the opposite is true. If we see blue shift, that means the wavelength of visible light is getting kind of squished or crunched. That indicates that the thing giving off light is moving closer to us, to the observer, and therefore the wavelengths are getting squished. Again, this idea is referred to as Doppler effect, and to wrap up here, I have a video that kind of highlights this concept for you.
Most scientists believe that our universe is expanding. That belief is based on an interesting property of light waves called the Doppler effect. Here's how it works. All waves travel outward from a source. A stone dropped in a pond, for instance, will produce waves that move out in a circular pattern from the splash. Light works the same way. When a camera flashes, light waves move out from the flash bulb. When the source of a wave is stationary, the waves can be thought to form circles radiating out from the source. But when the source is moving, something very interesting happens. The waves ahead of the moving source are bunched closer together. The waves trailing behind the moving source are spread out.
We hear this effect when a moving car blows its horn as it passes us. We hear a high-pitched sound as the car approaches us because the motion of the car bunches the sound waves closer together. When the car passes us, we hear a distinct drop in pitch because the sound waves are now spread out by the car.
Light waves show a similar shift. If a source of light, like a star or a galaxy, is moving toward us, the light waves are bunched together, and we see the light with a slight bluish tint. If the star or galaxy is moving away from us, the waves are stretched out, and we see a reddish shift in the color. Because all galaxies show a red shift in the color of their light, this is evidence that they're moving away from one another. So the red shift is evidence that our universe is expanding.